This video is about properties of expectation, and we're gonna provide proofs with discrete random variables in this video. Even though we provide proofs with discrete random variables, those results hold true for general cases. Those properties hold true for any random variables. We know expectation assigns numbers to random variables. If we regard expectation as a special function from random variables to numbers, what are the properties of this function? Let's take a look at the first property, linearity. In the following, we're going to assume all expectations are well-defined. We know for some random variables, they don't have expected values. But here we assume all expectations are well-defined. So all the random variables we discuss in the following, we're going to assume they have expected values. Okay, so for any real valued random variables, x and y, and any constant, the expectation gonna satisfy the following two identities. The expected value of x plus y is a function of x and y, it's a new random variable, and the expectation of this new random variable is equal to ex plus ey. So the expected value of the summation is equal to the summation of the expected values. And expected value of this random variable c times x. Cx is a new random variable generated from the x by multiplying c with x. The expectation of this new random variable cx is equal to c times the average value of x. We know if we have a function satisfy the following two conditions, fx plus y equals fx plus fy, and if fc, a scalar times x, a constant times x, equal to c times the function value of fx. If a function satisfies those two conditions, we would call this as a linear function. And look at here, for expectation, we have exactly the same structure, so the expectation is a linear function. In the following, we're gonna focus on the proof of the first identity here, because the second one, if we consider for discrete random variables, you can easily verify this by the definition, right? Suppose we look at the expected value of Cx if x is a discrete random variable, then the summation goes through all possible values of this x, which is exactly c times xi, probability value of x equal xi, which is c times the expected value of x. So the second statement is easy to prove, but the first statement may take a while. Let's take a look at the first proof with discrete random variables. Well, the formula looks a little bit messy and lengthy, but bear with me, it's actually quite simple to go through everything. I will be a little bit slower here to make sure you can follow. So the first, let's start with the expected value of x plus y. We know x plus y is a new random variable. So according to the definition, this expected value is equal to a weighted sum of all possible values could be taken by this new random variable x plus y. It's a weighted sum, so c should be multiplied by the probability value of x plus y equal to c, right? If we look at this event, x plus y equal to c, it's essentially equal to the union of a from the support of x equal to a, y equals to C minus A, right? So therefore their summation will be equal to C. And this is a union of mutually exclusive events. The probability of this event according to the axiom of probability is essentially equal to the summation of the probability of these events, right? So this one is equal to the summation of this. This is the first equality here. Okay, let's move on to the next one. Let's move C inside, and if the summation is well defined, we can interchange the order of those two summations. This gives this equation. Now note here, let's rewrite C as A plus C minus A, which is the value taken by X and the value taken by Y. And their summation. Here I didn't do nothing special, but only decompose C as A plus C minus A, which is again equal to C, right? Now let's denote B equal to C minus A. And given C gonna go through all possible value could be taken by the summation of X plus Y, it essentially means this B value should exhaust all possible choices within the support of Y. So C goes through all possible values. That essentially means here, this B gonna go through all possible values, which will be all possible values taken by Y. Now we split this summation. After we have this equation, let's split this summation into two parts, which is A times this probability and B times this probability. Okay. For the first term here, let's move A forward, and the value of these double summations remains the same. Let's take a look at the summation here. We're gonna sum over all possible values within the support of Y. And what is the note? Each of these events for different choices of B will be mutually exclusive event. Okay, this is the first term. As for the second term, this is what we're gonna do. We first exchange the order of the summations if the summation is well defined. If we change the summation order here, the value should remain the same. And then we move B forward. Okay, this is what we're gonna deal with the second one. And here again, we're gonna look at a summation where we're gonna sum all possible values, or sum over all possible choices of A from the support of X. Let's focus on this value first. What is this summation? Well, look at the summation. Inside here, the event. For different choices of B, we're gonna have a mutually exclusive event, right? So we look at the summation of X equal to A, Y equal to B, with B goes through all possible choices within the support of Y. They are mutually exclusive events, then according to the axiom of probability, we know the summation of the probability values is equal to the probability value of the union of those events. With B goes through all possible choices of the support, X equal to A, Y equal to B. But given here we're gonna go through all different choices of B, right? Let's rewrote this union a little bit. So it's a joint event x equal to A, intercept y equal to B, right? But what is this union? Let's rewrite it a little bit. It's essentially gonna be the event x equal to A intercept with the union of B goes through all support of y, the event of y equal to B. Look at here, this union is essentially the sample space. So in the end, we are calculating the probability of the event x equal to A intercepts with the sample space, which is the event itself. So the summation here essentially equal to the probability value of the event x equal to A. Same goes with this summation. It's exactly the same logic. The summation of the probability value here, given we are going through all possible choices of A from the support of X, essentially this summation of this probability equals to the probability value of the event y equal to B. So we are arriving at the second last equality. Look at the first term is essentially equal to the expectation of X, according to the definition of the expectation of discrete random variables, and the second one is the expectation of Y. So we provide a proof here with discrete random variables. Let's consider another proof. Now here we add an additional restriction such that the sample space only contains finite number of outcomes. Well, we consider this restriction to simplify the procedure and avoid unnecessary difficulties. Okay, so here we have finite outcomes. Well, the result holds true even we relax this condition a little bit, but if we work with finite outcomes, the proof is much easier and understandable. So let's keep with this restriction. Now, according to the definition of expectation, we have discrete random variable here. X is discrete, Y is discrete, and their summation will also be discrete random variables. According to the definition of expectation concerning discrete random variables, we have the first equality here. This expectation is equal to the summation over all possible values, say, could taken by this new random variables x plus y, right? Now let's decompose the event x plus y. This event essentially is the union of all possible of all outcomes such that x plus y, this random variable, would map those outcomes to S, and it contains all such outcomes, right? So it's a union of all those events. Each event only contains a single outcome here, outcomes such that satisfies this condition. X plus y map those outcomes to value C. Okay, and those are mutually exclusive events. So according to the second axiom of probability, we know the probability of this event is essentially equal to the summation of the probability of each of these events. Right? Now we move from this first equality to the second step. This summation is essentially equal to the probability value of x plus y equals c. Now let's move from the second one to the third one by moving c, interchange the order of c and this summation. Okay, now we move to the third step. Look at here. Here we are summing over all possible outcomes such that x plus y maps those outcomes to value c, which essentially means xs plus ys, those random variables, if we consider those are functions from the sample space to numbers, then the sum of those two numbers will also equal to c, right? According to this. So now we arrive at the fourth step. Let's move from the fourth to the next step. Here we're gonna sum over all those outcomes such that x plus y maps all those outcomes to value c, but at the same time we're gonna map sum over all possible choices of c. That essentially means we're gonna sum over all outcomes within the sample space. Next, let's decompose the summation into two parts. The first part is xs times the probability of this event containing only one outcome, and ys multiply exactly the same probability values. Now for the first term, let's regroup those outcomes. We're gonna group outcomes together if those outcomes are mapped by the random variable x to the same value a. And we're gonna sum over all possible values taken by this random variable x. So the first term can be rewritten in this format. Applying the same logic, we will rewrite the second term in this format. We're gonna regroup outcomes by different values. The y function would map those outcomes, right? If ys equals b, we're gonna group those outcomes together, and we're gonna sum over all possible values taken by this random variable y. Essentially, this term and this term, they take exactly the same value, and this term and this term, if the summations are well defined, they also equal to exactly the same number. Now let's take a look what happens to this summation. We know those events or those outcomes are mapped by x to exactly the same number, a. So let's just write a here. And what is the summation of s from s, xs from a, the probability value of this event, s? Look at here. Again, it's a summation of probability value of events that are mutually exclusive according to the axiom of probability. We know the summation of such probability will equal to the probability of the union of these events. And if we look at those, if the union of those events is essentially the events of x equal to a, because those are the outcomes that x would map those outcomes to number a. That is essentially the event x equal to a, which contains all the outcomes such that x would map those outcomes to value a. So if we write a here to replace xs and move a forward here, and the summation of the probability value here is essentially the probability value of x equal to a. And the same goes for the second term here. The value of this term is essentially equal to the same number of this summation. Now, what is the first term here? That is essentially the expected value of x. And what is the number here? That is essentially the expected value of y. So for the second proof, we also show that expected value of x plus y is equal to the expectation of x plus expectation y. Those are very abstract discussions. So let's take a look some example to visualize this linearity idea. If we throw a coin for one time, x denotes the number of heads because we only throw for one time, so it's either 0 or 1, right? What is the expectation of x? You can pause the video here for a moment and think about it. It's half. Now, what is the case if we throw 2 times? What is the expectation of y if y denotes the number of heads that we throw a coin for 2 times? Well, a fair coin here. That's gonna be 1, which is 2 times half, right? And what happens if we throw a fair coin for n times? Let's say n denotes the number, denote the number of heads. What is the expectation value? Expected value of that n? That's gonna be n times half n over 2, right? So this is a simple example to illustrate the case that if we have a random variable x, and here is throw for 1 time, throw for 2 times, then it's essentially should be equal to ex1 plus ex2, right? If we gonna throw for n times, that's gonna be x1, throw for a second time, third time, until n times. And it's gonna be the summation of ex1 until exn. Note, if we use xi to denote the number of heads in the s row, xi they have identical distributions. And we know distribution determines expectation. So all those values, right, are equal to half in this simple example. So in the second case, we have 2 times half. And if in the third case, when we throw n times, that's gonna be summation of half n halves. So that's gonna be n times half, right? This is a simple example to illustrate the linearity property of expectation. What is the second expectation property? The second property is monotonicity. Again, we assume all expectations are well defined. So here, for any real valued random variable xy, such that x is larger or equal to y with probability 1. So the probability of x larger or equal to y is equal to 1 here. Then we will have the expected value of x larger or equal to expected value of y. This is a very natural and intuitive result we have given the expectation, right? Summarize the average idea. If x is always larger or equal to y, then the average should also be larger or equal to y, right? And here, the equality will hold if the probability of x equal to y equal to 1. This is also very intuitive to understand. If those two random variables equal to each other all the time, then the average value, they should also be equal to each other, right? So it's a not only linear but also monotone function. If the argument increase, right, if x larger or equal to 1, then the function value will also increase. The expected value of x will larger than expected value of y. These results can be extended to more general cases. If we consider any real valued random variables x tilde, y tilde, if they have identical distributions with x, y respectively, such that x larger or equal to y with probability 1, then we would have expected value of x tilde larger or equal to expected value of y tilde. Now let's consider a proof of the above results with discrete random variable. Note that if we consider the difference between x and y, denote this difference as the new random variable z, right? Because that is simply a function of random variables x and y. Notice this that will be a non-negative function. It only takes non-negative values with probability 1 given we know x larger or equal to 1 with probability 1. Given x larger or equal to y with probability y, we know this difference will also be larger or equal to 1, larger or equal to 0 for all possible outcomes. So according to the definition of expectation of discrete random variable, we know expected value of that is essentially a weighted sum of non-negative values. Then expectation of z is apparently going to be larger or equal to 0. And we know z is essentially equal to the difference between x and y. And according to the linearity of the expectation, this is essentially expected value of x plus the expected value of minus y. But minus 1 is a constant. Again, according to the linearity, is essentially equal to expected value of x minus the expected value of y. So we have this identity, and apparently expected value of x minus expected value of y is larger or equal to 0. Now, if we have the expectation of x equal to ey, then we know expected value of that should also be 0, right? But according to the definition, it's a weighted sum of all possible values could be taken by z times the probability here. Given here we are working with the zi, small zi from the support of z, we know the probability is larger or equal to 0. And zi here, given we know z is non-negative, zi has to be larger or equal to 0. We know here for all possible values from the support, they have to be 0, because otherwise we will have the expectation of z larger than 0, which will violate the condition here. So if we have expectation x equal to expectation y, then expectation z is also 0. then all the possible values taken by z they have to be 0, right? If that is equal to 0 in this case, we know the probability of that equal to 0, because that's the only possible value taken by that, is equal to 1, which delivers the final results that the equality only holds true if x equal to y with probability 1. Then we have finished the proof with discrete random variable. Let's take a look one example to visualize the idea. Here, let's throw a fair coin for 2 times. Let x1 denote the number of heads of the first row. x2 denotes the number of heads of the second row. Here is a typo here. Second. So x1 denote the number of heads of the first row. x2 denote the number of heads of the second row. They both follow Bernoulli distribution, right? x1, x2, they all follow Bernoulli distribution. Half and half. At the same time, we know they are independent from each other, so we have IID distribution. Identical and independent and identically distributed, with Bernoulli half. Is half getting head, half getting tail. Let z equal to the summation of those x1 and x2. So that denotes the number of heads of the 2 rows. You can pause the video here and think about what is the relation between z and x1. Apparently here x2 either takes value 0 or 1, right? If we denote them as Bernoulli distribution, and equal to 1 only if you get head, otherwise 0, then x2 is a non-negative. So z as a summation of x1 with some non-negative random variables, x2 only takes non-negative values here as 0 and 1. We know with probability 1 that will be larger or equal to x1, because x2 only takes value as 0 or 1. And what happens to the expectation of that and the expectation of x1? Apparently, we would have the average value of that larger or equal to the average value of x1. You can calculate by definition directly, and indeed, this one will be 1, and this one will be half. Now let's consider a second case. Let y denote the number of tails for the 2 rows. Note that there is outcome s such that the ys will be strictly smaller than x1s, right? The s could be the outcome that we have 2 heads out of the 2 rows. In such case, then ys is equal to 0 and x1 is equal to 1. So here y is not larger or equal to x with probability 1. But what happens to the average value here? You can pause the video at this moment and try to figure out yourself. Y and z, they have exactly the identical distribution, right? They have the same distribution. In this case, if you calculate directly, you'll figure out that the expected value of y is still equal to 1, because it's half probability to get a tail each time, And if you throw 2 times the expected value of y, the expected value of the number of tails is exactly equal to the expected value of the number of of heads, which is also equal to 1. It's apparently larger or equal to the expected value of x1, right? This is because distributions would determine expectations. Here we have expected value of y apparently equal to expected value of z because they have identical distribution. And because we have the expected value z larger or equal to expected value x1, we will have also expected value of y larger or equal to the expected value of x1. The first results we can get directly from the monotonicity. And as for the second one, it's not derived from the monotonicity directly, but if we notice y and z have identical distribution and distributions determine expectations, then combined with the monotonicity, we can deliver the same results here. Of course, it's easy to check all the results and verify all the results by the definition of expectation. Now, this is the example for monotonicity. And apparently, for the monotonicity, the results we can extend it to general cases, at least shown from this example. Thank you for watching this video.